Hello, we did our project on supply chain networks and their dynamics. Since the start of the COVID-19 pandemic, we've seen how important having a robust supply chain is. Sometimes we have a cause we can point to, like how a cold snap in Texas brought its grids to its knees, or just how one big ship blocked one canal and almost took out the world economy. Other times there are effects that build on itself, like semiconductors are necessary for all modern electronics and have affected everything from hydroponic sensors to cars to the PlayStation 5. It's also not just affecting massive corporations, but small businesses too, like how a running cream cheese is ruining New York bagel shops. These issues can come from all over the place. It could be infrastructure-based, like how ships need to wait outside the port of Los Angeles for 2 weeks because there are not enough cranes. It could be because of the business model, like how lean or just-in-time manufacturing have assumed we'll always be able to produce exactly how much we need all the time, and now we're seeing the effects of not having backstock lying around. Lastly, it could be location-based. If all the world's semiconductors are made in one factory, for instance, it would be a big problem if that one factory got COVID. In this project, we're going to be looking at two different types of supply chains, a milk production chain and a power grid, and seeing how and where they break down, measures we can implement to prevent it, and in the end, whether or not there is a best supply chain structure.
So in order to test these questions, we decided to generate synthetic networks rather than use real-world network data. However, the synthetic networks that we ended up generating are based heavily on research that we did into what the shapes of different supply chains look like. So in order to generate synthetic networks, we had to make several assumptions about how supply chains work. For one, we assume that there are only 3 layers in the supply chains, going from producers to processors to consumers. In reality, different supply chains have more than this, more layers than this, but we just wanted to simplify it so that it could be generalized to more kinds of systems. Other assumptions that we make are that there aren't any multi-edges between nodes, that the flows only go from producers to processors to consumers, that within a layer, there aren't any edges between nodes. And then finally, that the distribution of degrees for producers and processors is drawn from power law distribution. So the two types of systems that we are focused on are an hourglass structure and a diamond structure. So the hourglass structure can best be thought of as a food system where there are a good amount of farms that are aggregated into a smaller number of processors and then many more consumers. By contrast, a diamond structure like an energy grid will have a smaller number of power plants or producers that are being distributed to a large number of transmission lines, which are then again aggregated to a slightly smaller number of load substations. And for the energy grid, we're ignoring the actual level of individual consumers. And so what we're trying to get at here is how different structures of different systems might affect the robustness to failures for the systems. So then another important element of the system that we have is the flows of the actual units of products. So producers generate a set amount in each time step and then uniformly distribute their product to all the processors they're connected to. Then the processors have a storage capacity, and then the storage capacity of the processors is drawn from a uniform distribution, so it's going to vary. We measure the amount of waste in the system as one of our key metrics, where waste is the amount of units that producers try to distribute to processors but are unsuccessful in doing so because the processors have reached capacity. And then finally, the processors will distribute their product to consumers, and consumers have a set demand level, consumption level, that is the same for all consumers, and they attempt to get that uniformly from all the processors they're connected to. And if they're unable to do so, we measure that as a supply deficit. The reason that we wanted to measure waste and supply deficit was so that we could then test how robust the system was to the deletion of nodes at different layers and by different methods.
So in testing our system, the number of nodes in each layer is constant for each respective network structure. And we want to find initial conditions to minimize the waste and amount of deficit in the system. After that, we want to delete nodes during simulation to find what characteristics contribute to the network robustness. So we see that when we increase production rate, processors reach a maximal supply, but then cannot pass on that supply to consumers because they have to turn away excess supply, which minimizes deficit and maximizes waste to a certain point. Accordingly, if we increase capacity enough, we're able to see that eliminating deficit is possible, but waste will reach a maximum proportion in the system. When we test the deletion of nodes, we will either randomly delete 10% of the producers or delete 10% of the producers with the highest degree. And when we test the deletion of the processor nodes, we can do the same tests, but we can also test the deletion of 10% of the nodes with highest capacity because that layer has that additional characteristic. So here we can see that the increase in production rate can only minimize deficit to a certain point, and that waste will maximize to a certain point and then remain constant. And then as we increase capacity, we can have enough excess supply to pass on to consumers, but waste will be minimized and then still be a characteristic of our system, unfortunately.
Yeah, so if we look at the results of the different ways of deleting nodes, which I'll refer to as the different attacks. So what we're looking at here is the supply deficit for the food network, which was the hourglass shape. And so the y-axis here is the supply deficit, which is when consumers wanted food but didn't get any because there was not enough flow through the network. So lower values on this chart represent better network flow. And so we can see that on the hourglass shape, attacks on the processor layer had the largest effect on network flow. And the most impactful attack was deleting processors by degree. So if we look at the diamond network, you can see that unlike the hourglass network, attack on the processor, or sorry, the producer this time had the largest effect. And similarly, the removing by degree was the largest effect. And so these charts show waste. And so you can see waste was actually much more consistent across the different attacks. But overall on the food network, waste was much higher. The y-axis here is the percent of waste compared to the total amount produced. And waste, again, is when the processor runs out of storage space, but the producers are still trying to pass them food or power. And so we can also see that in the power grid, the variation in waste was much higher. So, but in either case, removing producers had the largest effect on waste. So when we removed producers, we saw much less waste. So in conclusion, waste will kind of settle. So we didn't see a big effect based on the attack. The deficit can be eliminated with adequate production rate and capacity. And then a robust system should have an even degree distribution in the layer having the highest density. So we saw that the degree attacks were the most impactful, and especially in the layer with the highest density.
Our future works that we came up with have to do with trying to make our system more dynamic, like trying to add layers within connections, specifically the middle producer section, not producer, yeah, producer. Section similar to how a grid would actually works in reality. If you then trying to go from producer straight to consumer, like how you would with a farmer's market instead of a supermarket, cutting out the processor altogether. And lastly, adding adaptive network features like rewiring in order to, if one node fails, pushing from instead of going to that node somewhere else and seeing how that would affect our system. These are our references.